The intermediate value theorem is a existence theorem. So it's going to say that something exists. It's not going to really find what that thing is for us. So I want to be kind of clear about that. So we're going to start off by writing the theorem, and then we'll kind of talk about what it actually means. So if f of x is continuous on the closed interval a to b, and f of a is less than some y value L, and f of b is larger than it, so L is in between those two. And it could be the other way around, where f of a could be the larger value of the two. Then there exists a value of c on the open interval a to b such that f of c equals L. So if I kind of make a picture to go along with that, let's see, I have some room up here. Let's go that. So what it means basically, it's kind of like, of course this makes sense, but let's talk about it. It means that we've got some interval from a to b, and I'll do the situation where it's higher for a. So we've got a point up here, we'll call that f of a. Remember that a is the x value, or an x coordinate. F of a really means a y, or a height. So that's f of a. So when I write f of a in here, I'm really talking about the y value. And then we've got for our b, we're going to say that it only goes to a height of that f of b. If the function's continuous, so it's a smooth curve on that interval from a to b, if I know that L is in between those, so if I'm looking for a y value that's in between those two y values, the corresponding y values for my endpoints of my interval, that's what this is sort of saying here, that L is in between them. It's either that or that, and the only difference is which one's higher. So we have the second situation here, where f of a is the largest, f of b is the smallest y, and L is somewhere in between. This theorem says if there's an L that's in between those two y values, then the corresponding x that produces that y, we'll call it c, has to be between a and b. Okay, and that only works if the function's continuous. So let's look at some examples. So we're going to look at this graph below, this piecewise. The first thing is there a value of c on the interval -5 to 2? So we're talking about from -5 to 2 closed. Oh, sorry, that was -2. -5 to 2. Is there a value of c on that interval such that there's an x in there somewhere where the y is 2? So when they say f of c equals 2, they're talking about the y value of 2. So that occurs, yeah, right there. Now the x where that happens is here. We'll call that c. We don't know exactly where it is, but we know one exists. This is an existence theorem. So the answer is yes, there is a c that falls on that interval from -5 to 2, for which the height, or its y value, is 2. So say yes, there is a value such that f of c equals 2. Okay, so that's not really the theorem. We're just observing on the graph. Okay, now we're going to talk about, can we prove it from the theorem? We have the graph, but just from the information given here. We're going to look at the graph and see if we can actually use the theorem. So does the IVT guarantee a value of c such that its y value is 2 on that interval -5 to 2? The answer actually here is no. The intermediate value theorem does not guarantee the existence of c on the open interval a to b. It's open because like the c can never be the endpoint. And sorry, I can use specifics here. We have an interval from -5 to 2. Why? Because there's two criteria that have to be met, and it doesn't meet the first criteria. And we'll say because the function, I'll just say f of x, is discontinuous at x equals -2, which is on the desired interval. So what we're trying to understand here is that, yeah, from the graph, looking at the graph, it absolutely exists. But the theorem, you cannot apply the theorem because on this interval, the interval we're concerned with, the graph is not continuous. So you can see this condition has to be met, first of all. The graph has to be continuous. So in this case, it was just by chance that it happened, that there was a c that had a y value of 2. But it doesn't have to by this theorem. I can show you an example where it doesn't. Is there a value of c on the interval -1 to 5? Such that that c has a y value of 2. So just looking at the graph, the answer is no. I'll say all the y values on that interval are negative. So I'll say they're less than 0. So there's no way there can be a positive one, a 2, right? We don't have a y value of 2, so we'll just say, so no c exists such that its y value is 2. So the way we say that is f of c equals 2. So there isn't one there just by analyzing the graph, but we're trying to also jump and apply the theorem. So does it guarantee a value of c? Of course it doesn't. The first criteria is met, though. That's what we're trying to point out here. So although f of x is continuous on the interval -1 to 5, f of -1 is -1/2. So we're checking those endpoints. What are the y values at the endpoints? And f of 5 is -3.5. And we're looking for a y value of 2. So we'll say f of c of 2 is not between f of -1 and f of -5. So those are the two criteria that have to be met. We did an example where each one is broken. Sometimes it's easier to see how it's broken than when it works. We'll do some when it works next. So we're going to say thus the IVT does not guarantee the existence of c on -1, 5. So by showing how it fails, we're coming across the two things that have to happen. So we'll kind of summarize those. So the first thing is that f of x must be continuous on the closed interval a to b, and f of c must be between the y values. So again, the second criteria, we're really talking about y values. Right? So f of x has to be continuous, and we're saying the y value we're looking for has to be between the two y values at the endpoints. It sort of makes sense when you think about it. If the y is not in between those two y values, right? So in this one, the y values were here, and what was our other endpoint? I don't know, somewhere down here. We kind of guessed on that when we said -3.5. So it was here-ish. So these are the y values of our endpoints, and the y value of our desired y value, I'm going to pick a different color, is up here. It's not between the two y's. So that's the second criteria. All right, so if these two things are true, then we can say IVT guarantees that the x value for our desired y value has to be on our interval from A to B. That's what's happening here. So let's see how to do it without the graph. So we've got a function here. The first thing is we have to show that it's continuous on the interval. So we're going to say f of x is continuous on the interval -1 to 3 because its only discontinuity, how do I spell this? I can never spell. Is that right? Yeah, I'll go with that. Is at x equals -2. So remember, discontinuities or whatever make the denominator 0. So I know that x plus 2 equals 0. If I solve that, I get x equals -2. So I know at -2 there's a discontinuity, and that's the only one. And thankfully, -2 is not on this interval. So we're good. It's continuous on our interval. Criteria 1 is met. Criteria 2, our desired y value, 2/3, has to be in between the y value at the endpoints. So what we need to do is plug in our endpoints into the function and see what we get. So I get -4 over 1. So I'm getting -4 for that endpoint. And for this endpoint, I'm getting 0 over 5. So I get 0. So the question is 2/3 in between 0 and -4? It is. So that means the intermediate value theorem will apply. So here's how we're going to explain that. So we're going to say we show the y values, and we're going to say, therefore, well, actually, I want to say it's between there. So let me see here. Oh, no, 2/3 is not between those because I have it backwards. Sorry, I'm thinking 0 to 4. From -4 to 0, 2/3 is not between those. So we're going to say, therefore, it does not apply. Sorry. Therefore, IVT does not, and we just want to restate what the theorem kind of says, does not guarantee an existence of C for which f of C is 2/3, because f of f of C is not between f of -1 and f of 3. Let's look at another one where it's not going to be applicable. It's going to break the other condition, I would assume. Yeah. So we're going to say we got to check the continuities on this guy. So we're going to say there's a discontinuity at -2. Is -2 on that interval? Let me think about this so I don't make another mistake. It is on that interval. So therefore, we're going to say that since f of x is discontinuous at x equals -2, f of x is not continuous on the interval. Therefore, the IVT does not guarantee, or we can just say is not applicable, I guess. Did I spell that right? Yes, I think so. Okay. Let's look at one that works so we can finally see how we do this. So it says it's on the interval from -2 to 1. So does this have any discontinuities? Well, it's an exponential function, so it's continuous everywhere. So we're going to say step 1, f of x is continuous on -2 to 1 because P of x. So it is P of x, isn't it? I wrote f of x. Because P of x is never undefined. Or we could say is continuous everywhere, whatever we want to say. Number 2. So the criteria 1 holds. Now we got to check our endpoints. So we're going to go P of negative 2. And we'll plug that in. So we're getting e to the 0, I think. Oh yeah, because, sorry, cosine's always, should mention, number 1, that cosine itself is always defined everywhere as well. There's no discontinuities there. So I plug in my negative 2, I'm getting e to the 0, cosine of negative 2. So that's going to be 1 times cosine of negative 2. Darn it. So we need a calculator here to get an estimate. Because we want to see, I'm rummaging through my drawer. Where's my calculator? Oh, come on. Yes. Because we want to see where if the y value, the desired y value is in between these y's, we need an estimate. So we got to do it in our calculator. I'm getting negative. Sorry, I'm sort of rushing this video. I'm kind of a mess here. Okay, so that tells us that the endpoint negative 2 has a y value of about negative 0.4. Now we got to check the other endpoint. So if we plug in a 1 into this thing, we're getting e cubed cosine of 1. So that's going to be about 10.852. So now I know the two y values that my desired one has to be in between. So they want to know, is there a c such that its y value is 5? 5 is indeed between those two numbers. So I want to say something like, since p of negative 2 is less than p of c, which is 5, I like to say what we're looking for, that 5 is in between p of negative 2 and p of 1. Since the y value is in between those two y values, we can say IVT does guarantee a c on the open interval a to b such that f of c is, what was it, 5. So that's what it says. That's our final statement. It just says, yeah, there's an x value that has a y value of 5. Seems like so what, but this theorem is important in other stuff down the road. We're going to use it, so you'll see when we come back to it. So that's what the theorem says. Now, in the instructions, it's also saying afterwards, find the value of c. So this is not part of the theorem. It's just a little practice with your calculator and stuff. So we want to actually find what c value. So I'll just kind of do this. So 5 equals e to the c plus 2 times cosine of c. So we want to find out what y value, what x value, what c has a y value of 5. So this is a little calculator practice. I have the answer done out already. So how would you solve that in your calculator? You're going to put 5 into y1. You're going to put this into y2, and then you're going to use intersect to find the c. So that would be the c value. So that means that f of, you don't have to write this part out, but I'm trying to summarize. Okay, f of that equals 5, because that's what it says, right? That's the x value that has the y value of 5. And we got 2 more to do here. So, step 1. Does this graph have any discontinuities? It does at 2, right? Is 2 on this interval? It is not, so I'm good to go. So we're going to say something like f of x is continuous on negative 1 to 1 because its only discontinuity is at x equals 2. So criteria 1 holds. Criteria 2, we got to do the y values at our endpoints. So f of -1, if I plug that in, I get what? -1 over -3, I'm getting 1/3. If I plug in 1, I'm getting -1. So is -1/2 in between -1 and 1/3? It is. So that means IVT will guarantee the whole thing. We just basically restate the theorem. So we're going to say since f of -1 is bigger than this time, because this is the bigger value, right? The 1/3 is bigger than the -1. So that's going to be bigger than our f of c, which is what I like to restate it so you know which one you're talking about. Like it's the y value of -1/2 is in between the y value of -1 and the y value of 1. Notice my signs are going in a different direction than last time. So since that's true, the IVT guarantees a c such that, a c on the interval, the open interval, -1 to 1. Sometimes I write a to b. You really should write the interval in there. A c on -1 to 1 such that f of c is equal to -1/2. So that's it. That's all the theorem tells you. Yes, there's an x value that has that y value. We're going to actually find out what that c is. So we're going to plug in, we want it to be -1/2, and we're plugging in c. So it's equals c over c minus 2. Let's do this one without a calculator. Let's do some practice solving here. I would probably cross multiply and get -c minus 2 equals 2c. -c plus 2 equals 2c. I add my c. I get 3c equals 2. c equals 2/3. So that would be my c. I can confirm it's got to be on that interval, right? It is on that interval. 2/3 is in between those two numbers. So again, that's not part of the theorem, this part down here. It's just a little extra practice. Last one, we've got ourselves an exponential function, so it's continuous everywhere. So we're going to say f of x is continuous. Is continuous on the interval 3 to 5 because it is an exponential function. Which has no discontinuities. This is the part that we can be uncomfortable with. You have to write all this out. You have to say it. We have to explain. The reader is assuming you don't know stuff. Like you have to, or I should say the other way around. You should assume the reader doesn't. You don't assume the reader knows the theorem. You have to state why it's continuous and why. Step 2. Let's check our endpoints. I do f of 3. I want to find that y value. So it looks like we'll get, -1/2. We're plugging in a 3, so it's going to be to the 0. Oh, that one's not so bad. This should be -1. I didn't see that -2, sorry. So then it's -2. So it's -3. So that's that endpoint. And then if we do f of 5, we're going to get -1/2, -5 plus 3 minus 2. That's going to give me what? -1/2 to the -2 minus 2. So I'm going to make that positive, flip that 1/2 to a 2. So now it's going to be -4 minus 2 is -6. So there's our two y values. Is the desired y value in between those two? It is. So that means IVT will work. So I'm going to say, again, since f of 3, I want to say the y value for c is in between these y values. So remember, f of 3 means the y value is, and that's going to be the bigger one because it's a smaller negative. F of c is in between those, and f of c we want to be equal to -4, I believe. Yep. F of 5. So since that's true, the IVT guarantees a c on the open interval 3 to 5 such that f of c equals -4. So that's what the theorem does. It says, hey, yeah, this guy exists. Can't stress that enough. It's an existence theorem. Let's go find the c. What c has a y value of -4? So we're going to say -1/2 to -c plus 3 minus 2 equals -4. I'm going to say we could do this either way. I'm going to say let's do calculator, right? So put that into y1, put that into y2, and you should get a c value of 4.